So I have a couple of things to say about the test, but we'll wait for a few more folks to trickle in. Let's just go ahead and jump in, and then we'll come back and talk about the test for a minute. So today is class number 13. Today we are doing trigonometric substitutions. This is the very last antiderivative technique that we're going to do the whole semester. So maybe that's reason to celebrate for some of you. I warn you that trig substitutions are ridiculously hard. And I just want to put out there, I care for each and every one of you despite what I'm going to put you through in the next 70 minutes, okay? Oh well. All right, after we do trig subs, we're going to spend a day on approximating definite integrals, 2 days on something called improper integrals, and then we'll get into our applications of integrals section of the class. Any questions on the calendar? Oh, and there's no project assigned until the 6th. I guess that's Monday coming up. So you're on like a mini vacation until I hand out that project on the 6th. Okay. So here we are on page 3. Today we cover another new integration technique, trig substitutions. Trig substitutions are integrals where we can substitute a trig function to simplify an integral involving a squared plus or minus x squared, where a is a number. So we're going to do one example here, and then you do lots of examples in the activity. But I just want to look at each of the examples real quick, so we're finding the common thread that makes this new technique, which we haven't covered yet, that makes it tick. So in this example, we've got the integral of 1 over square root of 9 minus x squared. If we were going to try u substitution, what's a natural choice for you? Just the 9 minus x squared, right? Just the stuff inside. What's the derivative? Negative 2x. There's no x on the top to cancel with that negative 2x. It's going to pop out in the bottom, right? So that u substitution isn't going to work. In fact, no u substitution is going to work. Parts is not going to work. Partial fractions, it's not a polynomial on the bottom, so there's no chance on that one. So we have no way to solve this one. But I just want to point out it involves a number plus or minus an x squared, right? 9 minus x squared. It happens to be inside of a square root. On the next page, you can stay where you are on your packet, but here is a 25 minus t squared. Again, same idea. It's inside of a radical. That's okay. This one is a plus, and also there's an x squared in the front, but the key here is a number plus or minus x squared, and then some other stuff floating around it that hopefully magically will all work out. The perfect squareness just makes the calculations a little bit easier, but even if this were 15, there would be square roots of 15 in the answer, which is okay. And then I think maybe one more. Yeah, right here, x squared plus 49. 3/2 power, like that's a square root and then cubed, but it's not so much about the power, it's about the form of the rest of the stuff. So number plus or minus x squared, that's what you're looking for this new technique here. Okay, so let's actually take a look at this problem here. Okay. All right, number 2, let's find the integral of 1 over square root of 9 minus x squared dx. We'll perform a strange substitution to make the integral tractable. Tractable just means manageable. Okay, so we've done plenty of u substitutions. We're going to do another substitution. It's going to look very strange. Here's what we're going to do, and you should write this part down. We're going to let x equal 3 times sine of theta. So for the moment, don't worry about where that thing came up with. I'll give you hints for how to pick that thing, but it's pretty easy once you have the hints. But I will say that this is similar to a u substitution. Don't write this part. But normally we start with something like this, right? Let u equal, and then we pick something that lives over there. Okay, so this is the same idea. I called it theta, leave it as theta in yours, but I mean, you know, it could be a u. And this is kind of strange to start with an x equals instead of a u equals, but you could solve this for u, couldn't you? Like divide both sides by 3, don't write this. And then how do we solve for u? Arc sine or inverse sine? Right, that's what I could have started with. Let u equal 9 minus x squared. Okay, that's not going to work. Let u equal inverse sine of x over 3. I don't know why, but it turns out that's going to work. But it's the same idea, right? It just turns out to be much more useful to write it in this form that's up here in blue, but it's equivalent to a standard let u equal thing that we've been doing for a while. Okay, so let's get rid of all this stuff here and proceed. Okay, what we're going to do is come up with a way to rewrite this piece right here. So go ahead and copy this part now. Just like with u substitutions, what we need to do is substitute everything inside of the original integral has to become something with u's in it. In this case, it's actually going to become something with thetas in it. Okay, 9 minus, what did we say x was equal to? So 3 sine of theta gets squared. Everybody see that? Okay, and then we're going to continue to clean this thing up here. 9 minus. So remember, we're squaring the 3 and also we're squaring the sine of theta. So this becomes 9 sine squared theta. Fair? This should give you an indication as to why I chose 3 here. It's because I wanted them to both be, I wanted to have a 9 at the end of the day. So I picked the square root of 9 up there. That was my 3. We're going to factor the 9 out of both terms, still inside the square root. What's left? 1 minus sine squared theta, right? Hey, we've seen that, right? 1 minus sine squared theta is part of a very famous identity. So let's just write it right up here. You guys know that sine squared theta plus cosine squared theta is always equal to 1. And so 1 minus sine squared is really cosine squared, right? And so this thing down here becomes square root of 9 times, instead of 1 minus sine squared, cosine squared. Okay. And that is why I chose to put a sign there, because I knew that it was going to become a 1 minus sine squared, which I could replace. Okay. Again, I'll give you hints, but that was the motivation, was to get to that simplified thing down there. Equals square root of 9 comes out as 3. Square root of cosine squared comes out as cosine. And we now have a simplified version of that denominator. That denominator is really just cosine of theta. Okay, so we're going to go back up and substitute, but there's one other thing we need to change. The other thing we need to change is the dx, right? I've got thetas, not allowed to have a dx in here. So let's do that calculation as well. What is dx equal to? Three cosine theta. Normally, you'd put a dx d theta, but we're going to put that d theta over on the right-hand side. We've done that a bunch before. So 3 cosine of theta d theta. Is that all right? So if we let I equal that original integral, then I equals, and now we're just going to put some stuff in here. So upstairs is a 1. Downstairs, that whole red thing became 3 cosine theta. The x became 3 cosine theta. They're not normally the same. It just sort of happens in this case. 3 cosine theta d theta. I'll circle that thing in purple, this thing in red, right? Everything in the original has become replaced with some equivalent thing in this new integral. Okay, equals. All right, so this is really the integral of what cleaned up thing? 1 d theta, right? And what is the integral of 1 d theta? Not x, but theta, right? That's the variable in this case. Theta, and then don't forget plus c and all of our things. And so that's our answer. The integral is theta, but theta is something we invented. This was a problem involving what letter? X, so we better end up back with x. So we have one equation in blue that relates theta and x. So we actually do need to solve this equation for theta so we can figure out what to put over there. So I'll put this in blue here. We did this before, but we need to do it for real now. We need to solve that equation for theta. And so inverse sine of both sides. And we get theta is really the inverse sine of x over 3. So that means that the integral I, which was theta plus c, is now really this thing plus c. Inverse sine of x over 3 plus c. And that's it. Antiderivative of 1 over the square root of 9 minus x squared dx is inverse sine of x over 3 plus c. And as usual, you can check. What do we have to do to check? Take a derivative of this and hope that we get that thing back there. You have to do just a tiny bit of algebra to clean up your derivative, but everything will work out hunky-dory. Questions on that? Okay, so the activity is on the next page. You're going to do another one just like this. I think the only difference is the 9 becomes another number, and then we're going to ramp up the difficulty. There's like extra hints. There's one more step that you normally need to take that we didn't need to in this one, but there's step-by-step hints written in that particular problem in the activities. Levi? Okay. Yeah. All right, so before you jump into the activities on the next page, let's just talk very briefly about the test, which I've just handed back. The median grade was 78. That means half of you did higher than 78 and half of you did lower than 78. High grade was 100, which is pretty darn impressive. So I wanted to say just a couple of things about the test. Number one, some of you, in terms of antiderivative techniques, are very much infatuated with integration by parts. And I know that when we have two things multiplied together in an integral, oftentimes you might think parts. One of them is u and one of them is dv, right? But really, what was the technique that was a lot more popular than parts? U substitution. And U substitution also often looks like one thing times another. And so I think some of us need to sort of let go of the idea that like parts is the be all end all. It isn't. Some of us applied parts to some U substitution problems that were intended to be straightforward, and you made them a lot less straightforward. I'm not a Facebook guy, but on Facebook, is there like still a status like box? Yes, so some of you need to update your status. It says like in an exclusive relationship with parts. Like I don't need any other integration technique. Parts has everything I've ever been looking for. So again, we gotta let that go. U substitution, much, much better. Okay, I mentioned this at the end of last semester in Calc 1. For some of us, there is a disconnect between the homework grade near 100 and the test grade not near 100. The important thing, the point of doing the homework is to learn the material. So please, please, please let go of the idea that I just need to do this homework so that Ian can give me a little 4 on that piece of paper that he walks around with every day. That is not the point. Much better to take some 3s or 2s or 1s on the homework, but really, really make sure you understand the homework problems that you do. Even if it's only a quarter or half of the homework problems that you actually do, take your time, do them right. Homework grade is not near as important as this test grade. And finally, I do encourage folks to try the problems that they didn't get here. Don't just take this and throw it in a binder and never look at it again. Some folks have already, like as soon as they walked out of the test, came back like a little while later. Oh, shoot, I want to, let me write down that integral. I want to try it later on. And then, oh, I got it now. And it's really important to have that moment where you just get it. And if you don't ever get it, or if you want to have me look at your work when you, just sort of retry these problems for your own benefit, I'm happy to just show it to me outside of class, okay? All right, I think that is that. All right, so on the next page, activities start right there. This begins with some guidelines for when to use which substitution. You guys can make a quick change right now. Change these t's right here to x's. both of those t's, you can just turn back into x's.